translation symmetry, right? Should be invariant under translation operation. So that is the key point about crystal. This is define everything, all the property you see, right? This translation symmetry should be invariant under translation. That's what. Now, so we can write this electron density into some sort of power series expansion. This is one mathematic way of expressing anything that you don't know really. So you can expand it in terms of this power series expansion. Sometimes it's called plane wave expansion because you can see you have the same form e to the I sort of k dot r kind of thing that you have, and this is like a plane wave form. So when you talk to physicists, they call this plane wave expansion. It's the same thing. It's essentially a Fourier representation of the same thing. You have an infinite sum of this plane wave with different parameter on top here, different frequency, if you like, of the plane wave to add up to some object that you have. Okay, it's very much like, if you are confused about it, it's very much like how do you get a photon from a bunch of waves. And one of the ways that you can think about this is essentially Fourier representation. So you have wave like this. This is my one of the wave. And then you can add another wave with a different frequency, like this, or different wavelength, right? And then you can keep doing this until, if you add all these waves together, what you end up is, typically a pulse like this, right? And this whole thing is what Einstein gave us. This is known as photons, right? Because if you add multiple plane waves together, you end up with just one pulse of the radiation. So it's very much like this idea that you expand any object into this plane wave to generate what you've got. So you can always do this, so-called Fourier expansion of these properties. Then, if you write this like that, so you have a sum, plane wave expansion, and some coefficient in front in terms of each of these plane wave. I write this little g vectors here because this is kind of my carrying point that different amount, this control the frequency, if you like, this little frequency of my photon. I can apply my translation frequency in here. Instead of writing r, I have r plus t, right? Work out the electron density of this one. And then I use my plane wave expansion again, and r plus t. And you just write out the mathematics. And what you see is something like this, n sub g e to the I dot r and times e to the I g dot t. So this is dot product of two vectors that you have. Now, so because that I have a crystal, because I must observe this invariant under translation property, this term and this term must be the same. In other words, this and this must equal. And in order for this to equal, you can see that this term, e to the I g dot t, must be equal to 1. Otherwise, I would not have those two the same. So e to the I g dot t equal to 1. And how do you get 1? The way you get 1 is that g dot t, this exponent, must be equal to 2 pi times some integer. Okay, so g dot t must equal to 2 pi integer in order to satisfy this condition, e to the I g dot t equal to 1. Okay, so that gives us and since t is my translation vector from one lattice point to another, right? So this is kind of my lattice vector because I always am moving from one lattice point to the next lattice point. G therefore has the inverse dimension of this translation vector because n here is an integer. Okay, so G therefore is called a reciprocal lattice vector. So this is how I generate my reciprocal space lattice. Okay, it's a kind of a difficult concept to grasp initially, but if you think a little bit more about it, then with time you feel more comfortable about the concept, right? About the concept. So think of it as reciprocal space, or think of it as momentum space. That's another way you can think about it. It's equivalent to momentum space. But of course, momentum space is also very hard to grasp. So we are a stationary object. We are Cartesian beings, so we like to think in real space, not in residual space. But let's see if we do some example. You may get more comfortable about this. Okay. Again, this is a residual lattice vector, and you can think in terms of this vector can be expressed in terms of its own coordinates, reciprocal space coordinate, and I write it as big A, big B, and big C. And you can write just like your normal space coordinate T here as some, just like this. I can write T as some integer times A, some integer times B, some integer times C. I can also write my residual space as some integer times A, some integer times B, and some integers times big C. And A, B, and C are the unit vector, if you like, unit vector in my reciprocal space. Okay? And fortunately, because of this relationship, you can work out, and I don't bother working, I just give you the data. You can work out that they are related to real space. So residual space, you can work out this A, B, and C, big A, big B, and C vectors from real space vectors. So for example, big A is a cross product of this the small b and small c, the real space vector of these two. So a cross product, what is a cross product? Well, if you're talking about b and c are orthogonal to each other, so you would have this the third vector, which is the A vector here, would be then orthogonal to both of these. So that's an example of a cross product. Now this bottom term is no big deal. This bottom term is a number. It turns out to be A dot B cos C. A dot B cos C. As it turns out, you look at vector algebra, it turns out that this is actually the volume of the unit cell, of the real space unit cell. So it's nothing more than some constant, right? Because 2 pi divided by the volume of the unit cell of the real space unit cell times a cross product B and C of the other one. So similarly for big B here is cross product to C cross A and so forth. And so if you are not convinced, what you can do is that you can take one of this and put it into equation star, right? You write this expression G dot T, so you have this dot this, right? And A, B, C are given by this, and you see that they come out to be 2 pi times some integer. Okay, so you can do that as an exercise. You can just simply say you can turn off these two. Let's say assume K and L is 0, right? You can assume K and L is 0. So your G vector is in the same direction as the A vector, and then you can find out what you got from there. In order how to get, if G is just A, what should T be? And you find out that it has to be something like this. Okay, so I'll let you think about this because it takes a little bit time to digest this. So there's no point for me to beat it to death. So I'll let you work on it a little bit offline. If you do that, what you could do is that you can think about the dot product of big A and big little a, residual space A and little a, and it turns out that if you do the dot product, it's equal to 2 pi here, and the other are all 0. Only the diagonal term is like the residual space of B times real space B is equal to 2 pi, and similar for C in here. And so that's the hallmark of that you have residual state, and the residual state lattice has the dimension of link to the -1. The -1 is missing here, so it's linked to -1 because you can see, right, any of these A, B, little a, little b, and little c have dimension of length, of course, and the product is 2 pi. So therefore, big A, big B, and big C are reciprocal.